Bases are very similar to acids in that you can have either a strong base or a weak base. Most of your bases are going to be strong bases. The weak bases list is much shorter. So if you're trying to memorize which ones are strong and weak, I would recommend memorizing a list of the weak bases because it's the shorter list. All hydroxides are strong bases. So they're going to react like is shown in the first example with 100% of that NaOH dissociating into the sodium and the hydroxide ions. Now let's suppose that we have 0.25 molar NaOH. Because 100% of it dissociates, that means we're going to get 2.5 molar sodium ion and 0.25 molar hydroxide ion. Now, if you're calculating the pH of this solution, it's relatively simple. Because this is 100% ionization, the pH is going to be related to the amount of this right here. Now, we know that pH is the negative log of the hydronium ion. Well, POH, there's such a thing as POH, and the POH is the negative log of the hydroxide ion. And another fact that you need to remember that makes solving this quite easy is that when you add the pH to the POH, you always get 14 because that's the way the scale is set up. So to solve this equation, it's going to be pretty easy. I'm going to calculate the POH first. And I just realized that I did something. I left out my O. All right, so I'm going to calculate my POH first. So in this, it's going to be equal to negative log of 0.25. So in my calculator, that's what I'm going to put in. Negative log 0.25. That's going to give me 0.602. So that's my POH. Now to get my pH is probably what the question is going to ask you to do. I'm just going to plug it into this little formula right here and say, and rearrange it, but it'll end up being 14 minus 0.602, and I'm going to have a very high pH, 13.4. And that's the pH of that solution, which, sodium hydroxide is a very strong base, so it will have a very high pH. Now, in the second problem or example that I've listed here, this is a weak base. And a weak base sets up an equilibrium. It's going to have a Kb, B for base. And I went ahead and looked up the Kb value for ammonia. Ammonia is NH3. And that's where I'm going to start. So in this example, I'm going to use the same amount just to show you the difference between a strong and a weak base, what it does to the pH, just like I did in the prior video with acids. So I'm going to keep this at 0.25 molar. And it does set up an equilibrium, so we're going to use our ice chart. The ice chart is going to stand for initial, the amount it changes, and then the concentration at equilibrium. So I have 0.25. I start out with 0.25. And some of this is going to attract one of those hydrogen ions. It's going to steal one of those hydrogen ions from the water and become NH4. Now, we don't know that how much ammonia does that. But the Kb value will give us an idea. And if you look at the Kb value, it's times 10 to the negative 5. So you're probably talking about a pretty small amount. we can calculate that. So the amount of ammonia that's going to do that is going to be minus X, because you're going to lose a certain amount of it to form ammonium. So at equilibrium, I'm going to have 0.25 minus X. This is 1 to 1, which makes it easy. So initially I have 0 moles of, or molar of ammonium and 0 amount of hydroxide. And both of those are going to increase by a value of X, as the ammonia takes away one of those hydrogens. So at equilibrium, I'm going to have X amount of ammonium and X amount of hydroxide. So when I substitute that into the Kb formula, I'm going to get 1.8 times 10 to the negative 5 is equal to X squared over 0.25 minus X. Now, just like in the last video with the strong and weak acids, when we calculated the pH of a weak acid, we noticed that this magnitude here of negative 5 is very small in comparison to this initial concentration. When you compare those two values, there's a big difference, which means this X minus X is not going to change that initial concentration by very much at all. That minus X is so small that when you calculate its value and subtract it from 0.25, you're going to get 0.25. It's going to round to 0.25. So we can just ignore that. And you can do that every time this Ka value or Kb value is less than times 10 to the negative 4. So beginning with times 10 to the negative 4, times 10 to the negative 5, times 10 to the negative 6, and so on, you can ignore this X value on the bottom of that fraction. So if I ignore it, then I'm going to have, solving for my X value, I'll end up multiplying 1.8 times 10 to the negative 5 times 0.25 and taking the square root of that. So you will get an equation that looks like this. That's all under the radical. And I'm going to put that in my calculator and solve for X. I get an X value of 0.021. Oops, no I don't. There's 2 zeros there. It's 0.0021. So like I said, X is very, very small. And of course this is an approximation, but it's just not going to affect that initial concentration that much. So if my X value is that, that's how much hydroxide ion is actually in the solution. That is your concentration of hydroxide. So I can take the pOH of this value and the pOH is going to be negative log 0.0021, and I get a pOH of 2.67. Now, the questions will usually ask you for the pH, not the pOH. So I'm going to calculate my pH value. I'll do it up here in white so you can see it. Just in the middle here. My pH is going to be 14 minus 2.67, and that's going to give me a value of 11.3 for the pH of that weak base. So if you're looking at the same initial concentration here and comparing a strong base to a weak base, you can see that those values are quite different. For that strong base, the pH is much higher at 13 than it is for the weak base at 11.